A theorem that is interesting is that I said that in the C-infinity category, when we are considering intersections of C-infinity submanifolds, these intersections can be very wild in general. But that's never going to happen in the presence of transversality. And that's one of the reasons that justifies its inclusion. Later on, we will see that there are other reasons, and one of them is that transversality is somehow dense. But let's go first with this theorem. Consider X and Y be two submanifolds of a differentiable manifold M. And suppose that these two submanifolds are transversal. We are going to use the same symbol for the transversality of a map and a submanifold and for the transversality of two submanifolds. And what we have is that X intersection Y is a submanifold of M such that the codimension of the intersection is the sum of the codimensions. Let's see that. So consider a point, all of this is local again. So consider a point C that belongs to the intersection of X and Y. And in order to simplify our setting, let's call A, let's denote by A the codimension of X and by B the codimension of Y, right? What happens here is that because of our construction, there exists a map G from a neighborhood of C in M, but let's write down M, to RA such that it is a submersion, okay, and that satisfies that locally the preimage of 0 is equal to X, right? We have that. And we know that the tangent space of big X at the point C is actually the intersection from J equal 1 to A of the kernels of the differential of G sub J at the point C, okay? That's G sub J is the J component of G, okay? G can be interpreted as a map G1, G2 till G8. So this is the situation that we have for X, but we have a similar situation for Y, okay? All of this again happens locally. So we're gonna have a map H from a neighborhood of the point C in the manifold M to our B that it's still going to be a submersion, okay? The preimage of the zero vector is going to be Y, and we're going to have that the tangent space to big Y at the point C is just the intersection from K equal 1 to B, which is the codimension of Y, of the kernels of the differential of H sub K at the point C, right? That's what we are going to have. Okay, what can we do with all these things, right? Let's try to put some order into all this construction. So here we write that the tangent space of X at the point C is this intersection of kernels of D sub D of G sub J, okay, at the point C, and a tangent space of Y at the point C has it can be written in a similar way. here kernel of the differential of h sub k at the point C. Okay, but we have to understand now that there is a formula that relates for two linear subspaces of a vector space of finite dimension, the dimensions of these subspaces, their intersection, and the sum. So this dimension of the sum of the tangent space of x at C plus the tangent space of y at C plus the dimension of the intersection of these two linear subspaces, okay, intersection, right? It's equal to the dimension of the tangent space of x at C plus the dimension of the tangent space of y at C. This is linear algebra, right? The issue is, we know, because of the definition of transversality, that this sum is indeed the tangent space of M at that point. So this dimension is the dimension of our ambient manifold. And we are calling it small m. And we know that X is indeed a submanifold of codimension A. So this dimension over here is M minus A, and the dimension of the tangent space of Y at the point C is M minus B, because B is the codimension of Y. As a consequence, what we get is that the dimension of the intersection of these two tangent spaces of x and y at the point C, by doing very simple calculations, is indeed n minus a plus b, right? But we know also that the intersection of these two linear subspaces is the intersection of the kernels of the differential of g sub j at the point C and the kernels of the differential of h sub k. Okay, here k from 1 till b and j from 1 to a. And at this point, we have everything that we need. On the one hand, the dimension of the intersection is m minus a plus b. On the other hand, this intersection is the intersection of the kernels of a plus b linear forms, of a plus b elements of the dual vector space of the tangent space of M at the point C. So if this thing happens, if the dimension is M minus a plus b, and this intersection is the intersection of the kernels of a plus b linear forms, is because these a plus b linear forms are linearly independent, right? We deduce that all of these maps at the point C, here it's A, and then we have to consider the differentials of H sub J, okay? All of these maps, there are maps from the tangent space of the ambient manifold N at C to R, are linearly independent. But we treated this case previously when we discussed submersions, and indeed this implies that when we consider the map, which is just consider G as the first component and J and H as the second component, this is going to be a map which is going to be defined in M, okay, and the target space is going to be R to A plus B. What we're actually saying by noticing that these maps over here are linearly independent is that F, big F, is a submersion at the point C. And so the preimage of 0, which is going to be the intersection of the preimage of 0 by the map G and the preimage of 0 by the map H, is just locally the intersection of X and Y. And since this map over here is a submersion, what we're just saying is that X intersection Y is a submanifold in the neighborhood of C of codimension equal to A plus B. And that's what we wanted to show. Let us consider a few remarks about transversality. The first one is that if we have a differentiable map and we consider a submanifold of the target space N, and the dimension of M plus the dimension of C is smaller than the dimension of N, then the fact that F is transversal to C implies that the intersection of the image of M by F and C are disjoint. And why is that? Is because if you have a point X in M with image of X belonging to C, and we have transversality, then this implies that the image of the differential of F at X plus the tangent space of C at the image of X is equal to the tangent space of N at the image of X. And the issue is that the opposite, the image of the differential of F at X, has dimension that is less or equal than the domain of definition, which is the tangent space of M at X. And that the dimension of that vector space is the dimension of M. So we get that this is smaller or equal than the dimension of M. This is exactly the dimension of C. And so if the dimension of M plus the dimension of C is smaller than the dimension of N, what we get is the dimension of this sum is smaller than the dimension of this tangent space, which cannot happen if they are equal. So we get a contradiction. So that means that this situation over here never happens. And so if F is transversal to C, in particular, the image of F and C are disjoint. Analogously, what we get is that if M and N are submanifolds of a differentiable manifold X, and the dimensions of these submanifolds have sum which is smaller than the dimension of X, then if they are transversal, in particular, that implies that they are disjoint. We have the same problem. In an intersection point, we get that the transversality condition cannot hold. And because of that, if they're transversal, there are no intersection points. The intersection is indeed disjoint. We are going to consider a few examples of transversality and non-transversality with pictures. Something that we have to take into account is that transversality of submanifolds depends on the choice of the ambient space, because the condition is a condition in which the ambient space is playing a role. The condition is that the image of the differential of f at x plus the differential of the submanifold at the image is equal to the tangent space of the ambient manifold at the point of f(x). So what the ambient manifold is, it's important in order to know whether or not, for instance, two submanifolds are transversal. In our first group of examples, we are going to consider curves in R2. That's going to be our ambient manifold. And of course, in the first example, these two curves are transversal because the tangent space to the first curve at that point, at the point of intersection, is going to be the line generated by that vector, and the tangent space to the other curve is the line, the tangent line to that curve, and these two tangent lines are in the difference, so the sum of them is going to be the plane. In the other two examples, the tangent space of these two curves at the point of intersection is the same. And because of that, these intersections are not transversal. But you can see that the intersections are kind of different. For instance, this one is very, very easy to break, to make the intersection disappear by moving a little bit the curves, whereas the other one is not so easy. And indeed, intersections can be of many different kinds. What we can control is the intersections of submanifolds when there is transversality. But if there is no transversality, it's quite difficult to know what happens. Now, let's consider another group of examples, the intersection of a curve and a surface in R3 in space. Here, we have transversality because the tangent space to the surface at that point and the tangent space to the curve are two linear subspaces that are transversal. The sum of these two subspaces is the total space. What happens in the two cases to the right is that the tangent space to the curve at the point of intersection is contained in the tangent space of the surface. And because of that, the sum of these two tangent spaces is the tangent space of the surface, and it's not R3. So in these two cases, we don't have transversality. Okay? Finally, let's consider the example of surfaces in space. In our first case, we are in a transversal situation. If we take a look to the tangent spaces to these two surfaces at a point of intersection, we are going to be in a situation which is going to be more or less like this. And of course, the sum of these two linear subspaces is going to be R3. What we have to realize is that if we have two surfaces, the tangent spaces to the surfaces are linear subspaces of dimension 2, and the unique way in which two linear subspaces of dimension 2 can have a sum that is not R3 is if they are the same. Okay, so either they are transversal or the tangent spaces of these two surfaces at a point coincide, which is what happens in all the other examples. This one, this one, this one, this one, and this one. In all of them, at the point that we're actually studying, we have that the tangent spaces to these two surfaces are the same. And the intersections can be very different. In here, the intersection is easy to understand because we know that the codimension of the first surface is 1, the codimension of the second surface, of course, is also 1, so the codimension of the intersection is 2. So that means that it is a submanifold of dimension 1, right? The intersection is a curve. In the other cases, the intersection can be very different. Here, it is a point. Here, it is a regular curve. It's a submanifold. Here, you can have even that these two surfaces can coincide in a very, very big set. Here, for instance, we are in a situation in which the intersection of these two surfaces is indeed something like this, something that is very far away from being a manifold. Here, at this point, we have a corner, but and it can be even worse. This example is not so badly behaved after all. So when we have transversal intersections, we can actually we know that the intersection is going to be a submanifold of the right dimension, whereas in the other cases, we don't really know what's going to happen. We said at the beginning of this lecture that general C-infinity maps are extremely difficult to study because, for instance, their zero sets are many times very wild. What we are going to do in general as a strategy in this course when we want to study differentiable maps is perturbing them a little bit so that they become generic in a sense that it's going to be precise later on, and then studying the properties of these generic objects, of these generic maps. Of course, a very interesting property for us is that the generic maps are dense, because that could actually allow us to implement this strategy. But it's also very interesting if certain of these properties, these generic properties that we are using, are also open. In other words, if for some topology that we are going to define too later on, these properties define open sets. In next lecture, we are going to have our first glimpse to this phenomenon, to open properties. Since we didn't define a topology in the space of functions yet, our approach is going to be simpler. We are going to use homotopies in order to determine whether or not two maps are close. Thank you for your attention.